is Shimo. I'm a doctoral student at the School of Information, University of Michigan. To start with, just a few words about why I'm giving this talk here today. So about same time last year, I was in a reading group at computer science department with some faculty members and students. We got together every week, read about neural networks and deep learning. And we came across, of course, Word2Vec, which is a popular word embedding model. And everyone knew that it was a very powerful model. But the problem is, a lot of us were having trouble understanding what was really going on behind the model. And part of the reason was that these original papers, they were nicely written, but they really did not explain in details how the model is working actually. So, for example, I was having problem trying to understand these figures in the original paper. So, what do these really mean? Is each box a neuron or a set of neurons? And are these boxes are they the same set of neurons or different sets of neurons? So these things are kind of confusing to me. And so I decided, why don't I write a paper that explains this model better than the original authors. So, quite fortunately, Word2Vec is open source. So I was able to read every single line of the original source code and figure out how the ring descent works, how the model structure is designed, and having some of my own intuitive interpretation of how the model actually works. So I wrote an article about Word2Vec parameter learning explained, and in the paper I created some figures that I thought to have done a better job at explaining what the model is actually doing, and that was pretty much it. And I put it on ArcSift and just moved on. And after several months, then you saw the paper online. He asked me whether I wanted to give a talk here, and I said why not. And when I started to prepare for this talk, I started watching on YouTube and videolectures.com to see some lectures about Word2Vec and other word embedding models. To my surprise, my figures have been used by a number of other people. For example, Christopher Manning, he teaches deep learning summer school in Montreal, and this summer he used my figure. This kind of thing makes me feel nice, although he doesn't really give any credit to me. Okay, so back to the main topic. Why do we need word embedding? In order for a computer to process natural language, we need to create representation for the language, oftentimes pre-representation for the words. And in early years, most of the natural language processing systems are using atomic word representation, which basically representing each word as itself or themselves. For example, Apple is represented by a vector of whose length is the same as the number of words in the vocabulary. So it's a super long vector, and only one component is one. This kind of representation creates a serious problem. So, for example, in the training data, you see Apple, Juice, they get co-occurring together, and in the test data, only using this kind of representation, there's no way to figure out, whether between orange and car, which one better fits that blank spot in the second box. And this doesn't really fit how human brains perceive these concepts. So imagine you or a human being sees a word apple. In a certain region of your brain, some neurons are excited and some others are inhibited. When you change that word apple to orange, we can imagine really few neurons change because they're quite similar concepts. But if you change that word to car, and significantly different set of neurons are excited. So this is kind of a continuous level of representing words at continuous levels of activations. Well, Mark talked about activation in the last talk. So, and this is called distributed representation. And what neural net embedding model have been trying to do is to computationally recreate such kind of representations. And how do they create such kind of representations? The idea is actually quite old. We want to represent a word by the context it appears in, so we can know the meaning of a word by the name of the kids. For example, we see apple and orange appears in similar contexts in a lot of sentences, but they differ a lot from car. So that's quite an old idea. But the idea of using embedding models is to preserve those kind of similarity relationships. So if, say, if a pair of words that are similar, in the contextual similarity sense, then when they are converted into low-dimensional representation, we should expect them to be close to each other as well. And as compared to other words, maybe say box, train, and car, they should be quite far away because they're distinct from those food or fruit. Okay, so yeah, so the recent success of word2vec and other word embedding models is they can not only do a better job at this, but also do something like this, which people at first when they see this result, they think this is kind of like a magic thing. To explain this, this is a very popular example of low-dimensional representation of words. So the idea is now they're not only able to preserve distance between similar words in low dimension, they are also able to preserve some certain kinds of relations in low dimensional space. For example, after you place these word vectors into low dimensional space, you can do vector subtraction, like king subtracted by queen would be equal to man subtracted by woman. And when this result first came out, people seemed really surprised. There must be some dark magic in this neural network technology, but later on people figure out it's just statistics. We'll talk about this later. All right. And here I listed some of the natural language processing applications that are benefited by word embeddings, dependency parsing, name entity recognition, and so on. And apparently word embeddings, why it is so successful is it is able to very efficiently train on very large scale data with very large vocabulary. For example, on the right I listed a table by the original word2vec authors. They claim that on the sentence completion task, they are able to do better than using word embedding than state-of-the-art methods. Okay. So now it comes to the question: why is, say, word2vec so powerful? Or maybe ask a different, or easier question: why is it so popular? Well, first reason, it comes from Google. Everyone loves things from Google. And secondly, it's an off-the-shelf end-to-end pipeline. You can just take it, download it online, and run it. Gives in a big chunk of text corpus, say Wikipedia, and wait a few hours, it can generate meaningful vectors. But the problem is, to a lot of people, to a lot of users, word2vec is a black box. What's the problem with that? If it works, it's fine. It gives you a good result, you're happy. But if something goes wrong, say you try something new, some new context setting or something else, and it fails or it doesn't give satisfactory result, you have no idea how to debug or how to figure out what's going on inside. So what I'm trying to do is to decompose this so-called complex or black box model into a white box model. As you can see, the actual model components are not that complex, so it takes an input, does some vocabulary building, context building, but the core thing is a neural network. And although it's not deep per se, and then it produces the weights between equal layer and hidden layers as word vectors as the final product. And so that part is going to be the focus of our talk today. And we have some more good news is that I created a visualization app for that. It's called WEBI. It stands for Word Embedding Visual Inspector. And it is online now. If you're in front of your laptop, you can type in bit.ly/webi-online. It's something, I think, first of its kind. And I'm going to do a demo of it right now. Okay, so that is word2vec running on my browser. And as you can see, on the top left is control panel, top right is the neuron. It's pretty familiar, one input layer, one output layer, and one hidden layer. And lower left are the matrices visualized. Input vectors are the weights between input layer and hidden layer. Output vectors are the weights between hidden layer and output layer. And here is I use PCA to do dimensionality reduction to visualize the actual vectors in the two-dimensional space. The blue dots are the input vectors, orange dots are the output vectors. And so you can also specify your training data here. Probably too small to see, but you can specify, what pairs of words you want as training data. So what input you want. It's just to learn, to predict what kind of output. The cool thing about this is you can actually train it. So say you specify input as eat, I want the output as the apple, and if you do whatever you can to actually do the gradient descent, stochastic gradient descent, to actually update the weights of input matrix and output matrix to actually make eat an apple closer, or make the probability of predicting apple higher. And then you can probably see the vector starts to move a little bit after every iteration. And if you are patient, you can train it, in batch mode, like from 500 iterations. After these iterations, it's running generic word to vec, it's the same algorithm, and you can start to see some of the vector patterns start to show. So in the weight representation, the more red, it is more positive, and the more blue it is the other way, more negative. And the neuron activation activity, so the red means excited, blue means inhibited. So you can actually hover over the input neurons to set each input neuron excited, and you can see which hidden layer neurons are excited and which output layer neurons are excited. In this case, you can see if given apple as input, it can predict juice. It can do whatever I specify input as the training data. So that's intentionally in the training data I specify to do this way. And if you specify drink as input, it can predict things that are drinkable. Specify eat as input, it predicts things that are edible, juice, drink, and so on. And you can even check, what if I combine these different inputs all together, and what kind of output is standard. It's pretty fun to see. So, any question about this? Yeah.
Why does it connect rice to milk?
Because I said so in the training data.
Oh, okay.
It only does what I do in training data. But rice milk is one good thing to drink.
So your training is only 2 words? The training is 2 words, right?
Yeah, training data is 2 words, but it also supports continuing back to words and escape from model. I will show you later on. Any other questions?
So sorry, the training data that you're specifying is not what WordPack normally takes, which is context windows. What is the training data you're specifying?
So the training data is exactly what the WordPack neural network portion is taking. The neural network itself will handle, sliding window across sentences and generating the context pairs. But the neural network portion of WordPack is identical to this. This is just in a smaller scale for you to easily interpret. Okay. So I want to dig a little deeper into how this model works. So Mark just talked about this. So just go through the flights through this really quickly. The basic neuron structure takes a set of inputs, weighted, and take the weighted sum. So we call the math is actually pretty simple. I call U as the net input of the neuron, and F is the activation function. So there are a couple of design choices that you can take in the activation function, either step function or sigmoid function, and so on. And we call this whole thing a neuron. So later on, we draw this neuron as a single circle. So how to train a single neuron? We've also talked about it in previous talk. You give it input and the expected output. This X is a vector. And you specify an error function. In this case, is Elton loss, and you take gradient, with regard to y, and then with regard to u, with regard to wi finally. So each step is using the gradient computed in the previous step, and finally you can know the update equation of the weights. Okay. So what can be done only using a single neuron? We'll also talk about that as well. So if you consider the inputs of this neuron as one-hot vectors, then you can consider consider it, learning a lookup table. So say apple, orange, car, paper, each of them can be only activated one at a time, and we will learn this kind of lookup table. Well, if you consider, continuous, values, and allow combinations of these inputs, then it's just basically a logic regression. Okay, multi-layer neural network. This is also not new. It's taking, hidden layer as the sum with the sum of the input layer, and hidden layer's output is, generated using an activation function, which is usually sigmoid, and the net input of the output layer is, weighted sum of the passed on input layer, hidden layer's output, and then so on. Okay, and how do we train it? We use backpropagation, and in backpropagation you also need to specify input and output. In this case, they are vectors. You define a loss function which can be L2 loss, and you take gradient, and so on, and so on, and so on, and so on, and so on. So my method. So we never to show equations in presentations, but here I'm showing equations anyway because I want to make 3 points. So the first point is actually very easy to make a mistake deriving these gradients. If you can easily mess up the indexes. And the second point is if you mess up the index, you're dead. It's pretty hard to figure out what's going wrong. And the third point is actually when programming this is kind of simple. For each of the derivation, it's just a for loop, and you actually coding out that interface. The back propagation part only took 10 minutes, but it took me 10 hours to figure out D3 and JavaScript and CSS stuff. Okay. So now we go from traditional or generic feed-forward network with one hidden layer to word-to-vec network structure. I will point out the difference. So the first difference is in the input layer. It is a one-hot vector. So each time. Well, continuous backward model may be slightly different. It can allow like 2 or multiple vectors, words to be activated. But for scaling model, it's a one-hot vector in the input layer. Only one word can be activated at a time. And in the hidden layer, the activation function is linear, so it doesn't do anything. It simply passes on the net input from previous layer and go on. So what this means is basically copying whatever word in the input layer is activated, copies its input vector, passes it on to the next layer. In the output layer, it has a softmax. What it does is basically generating a well-defined probability distribution, which is multinomial. So I will show this probably easier. It is easier to see with a word in activated. As you can see, the weights for the word orange is selected and populated in the hidden layer, and it is passed on, computing the activation level of each of the word in the output layer. So that's the figure in my paper. The mathematics is kind of simple as well. Hidden layer is basically taking the input vector. The net input of the output layer is doing the product of this hidden layer's value with each of the output vectors in the output layer. And then finally, softmax is what this is. Basically, computing this and normalizing it so that after summing over all the output nodes activation level, you will get 1, which is a well-defined probability distribution. And if you substitute use definition in it, you can see for each. So given this input, the probability generating each output is basically doing the product of these input vectors with output vectors, output words vector, and normalizing it. So if that's still not intuitive enough for you, you can understand it in a way which is like this. So given this activated word orange, how do we compute the activation level of apple? We basically take the inner product of input vector, input words vector orange, and do inner product with apple's output vector. In this case, they are pretty different. So you see, apple is actually quite light, not so much activated.
I thought
I'm sorry. So input words, input layer is 1 half encoding. So what is passed on into the input is, see, all of the neurons are 0 except orange is 1.
Yeah, so the input vector is actually the hidden.
Here, by input vectors, I mean input matrices in between the input layer and hidden layer.
To the hidden layer, right? So
Yeah, to the hidden layer, and that can be some messed up terminologies. Okay, and yeah, so and we move on. Yeah, so we're basically doing the inner product, between origin and all the other words to compute the activation levels, and I'm doing some normalization, of course. And you see that orange input vector and juice output vector are quite similar: blue, blue, red, red, blue, 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 red, red, blue. And so that's why the juice is quite activated in the output layer. Okay, and if that's still not intuitive enough, you can do dimensionality reduction and display the vectors in the low-dimensional space. So I'm using TCA, and you can see actually where the vectors are. Next question.
We have just 1 second. There are 2 vectors for drink
Yes.
and 2 for water.
Yes. One is input vector and one is output vector. Like this. Okay. Yeah. So how do we treat it? Pretty similar to generic free-form network. We do back propagation, and since we use softmax as the way of as the output layer, we define the loss function to be the minus log probability of that softmax of the output word we select, and we do gradient descent over net input of output layer over output weights over hidden layer, and then finally over the input weights. So that's pretty much similar. But I want to point out some intuitions of the updating rule of the output vector. So this is the updating rule of the output vector. You see, so it's basically taking the original output vector's value and subtracted by EJ is the prediction error of the output node, and H is the value of the hidden vector. What this means is, so suppose we have set drink as input and we want milk to be predicted as output. What this means is, how do we update the vector of milk? We want it to be more similar to drink. So what this is doing is adding a portion of drink to milk, as updating. And also we need to update all the other words output vectors as well. So for all the other words that are not selected as expected output, we subtract a little bit of drink from that word vector, so that these vectors that are not selected as the expected output will be more different from drink after the iteration, after the gradient descent. Is that clear? Okay, so on scatter plot, you can intuitively understand this. So drink's input vector is here, milk's output vector is here. After this, gradient descent, milk will get closer to drink, kind of gravity, like gravity, and all the other orange dots will get farther away from drink. And the intuitive understanding of the updating rule of input vectors is this. It's a little bit more complex, but the understanding would be the input vector will be subtracted from a weighted sum of the prediction errors. What this means is we're going to update this input vector drink as well, and it's going to move in a direction so that it's going to be closer to the expected output, but farther away from all the other words. So this kind of reminds you, as I said, gravity or strings pulling like word vectors based on the string's strength. And what is the strength of the string? It's actually co-occurrence, maybe inverse of co-occurrence, and we're going to talk about this later actually. Yeah, and then when they reach equilibrium, you get a stabilized word vector representation. Okay. Any question? Yes.
You say co-occurrence, is it just being near, or is it their presence in the phrase, or
Their presence in the same context window.
how big is that window usually?
That needs to be decided by the context builder, which we haven't really talked about yet. Yeah.
So when you actually go to use the word embeddings, you're using the output vectors?
We usually take the input vectors.
You say the input vectors.
Input vectors. The weights between input layer and the layer.
Is there any information in the output vectors? Like what
Yes, there are.
So
Actually,
what's the reason you take one versus the other? I guess I don't.
I guess there's some theoretical choice.
Okay.
Yeah. Okay. And so we've talked about the main thing, the engine of Word2Vec, and I want to move on to talk a little bit about the so-called continuous stack overword model and scapegram model. These are just different ways of generating the contexts or the inputs and outputs and expect outputs to the neural network. Method one, continuous stack overword, basically taking a word as target and then using the word surrounding it as context to predict it. Method two, scapegram is the opposite. So the Webby demo actually supports both. We switch to continuous stack of word. It's basically taking multiple inputs at a time and one output at a time. And you can train and see how multiple vectors are being updated. And the scapegram model is taking one input and multiple outputs, expected outputs. There's some mathematics details going on, but we're not going to talk about it today. Any question? Okay. So let's consider, context builder and parameter learning all covered. Next, let's talk about the training efficiency. So as you can see, suppose we have 1 million words in our vocabulary, and then it's going to be very inefficient to train which vectors? Input vectors or output vectors? Output vectors. Because in the update equation, given an input and an output, we have to, during the gradient system, we have to update every single vector and every single output vector, but only that one input vector. But this still creates a problem. Say you have 1 million words in your vocabulary, you have to, for each iteration, each training instance, you have to update 1 million vectors. That's a waste. That's takes a lot of time. So there are two, yes. So there are two ways proposed by the authors to optimize this computation. One way is hierarchical softmax. The structure of hierarchical softmax is like this. We, instead of associating each output vector with a word, now each output vector is sort of considered be in a binary tree. And the output vector is not making a prediction about how probable a word is. It's making a prediction whether you want to go this way or go that way in the tree. And let's define, say, red or activated is going up, and blue is going down. Then in this particular vector, say red going up, blue going down, and this predicts juice, has a very high probability. So the benefit of this is that if you want to do error propagation, then say juice is the expected output, and you want to do error propagation, then you only need to care about these 3 nodes, and you don't need to update the vectors of the other nodes. That's sort of convert n to a log n problem. It's sort of efficient. Yes.
How is that tree constructed?
That tree can be any binary tree, but the fact is Word2Vec software uses Huffman tree just for efficiency. The tree actually don't need to be explicitly constructed. Just layout this way, just have our mental model interpretation of the models, how the models work. Each node is still fully connected with the hidden layers. These links do not actually exist. Okay, And negative sampling is a completely different idea. It's basically saying, given that input and this expected output, I will still update the output vector of this word. But for the others, I don't bother to update all of them. I will just do a sample. I will sample from the negative samples words, hence the name negative sampling. And there are some more mathematical details going on, which we'll also not talk about. Is that fair? So we've covered the majority of word2vec and some interpretation about how the model actually works. And I bet I showed repeatedly this heat map of weight matrices. I bet that rings a bell to a lot of you. If you wrote it, and then does it remind you of matrix factorization? And indeed, it is. word2vec is indeed implicitly doing matrix factorization of the coherence matrix. And there's a paper by Omer Beauty and Yoav Goldberg about this. They have mathematical details saying that the Skip-Grad model with negative sampling is actually doing implicit matrix factorization, and the matrix is a pointwise mutual information. Although they have to modify the definition of pointwise mutual information a little bit to fit the reality of word2vec. And later on, they have this ACL 2015 paper, in which they show that carefully constructed matrix factorization can have word embedding, can produce a word embedding that has equally good quality as produced by word2vec. Okay, and there exist other kinds of neural embedding models like these one. I will not talk about them today, but I do want to talk about more on word analogy. First of all, it is not something new. By word2vec in 2005, in the year of 2005, these guys from Microsoft have already produced results that can generate, analogous relationships between words like swim, swimmer, learn, student, teach, teacher, and so on. And here, more syntactically related, shown, taken, showed, taking, these kind of things. And in my demo, I also created our favorite example showing that how word analogy, the famous analogy, king, queen, man, woman can be reproduced. So let's run it 1,000 times. Usually it gets very good results. The fan. It was not like running this crazy on my laptop. So one thing I want to point out is why these are so light, because they never appear in my training data as context word or input word. So these vectors never got trained. So let's update the PCA, and let's look at only the input vectors of man, woman, queen, and kings. Here's king, here's queen, here's man, here's woman, so you can do the vector subtraction. That sort of proves the idea you can recover the word analogy using word2vec. Is that okay? Okay. Miscellaneous embedding, what does that mean? So far all we have talked about is given a word, predict a word. That's what NLP people like. But you can do a lot of alternative things. So given a user as input and predict a tweet, this way you can get embeddings to users, embeddings to tweets. Given customer, predict a product or item, so you can build a recommendation system, where you have customer embedded, product embedded. This is kind of like a singular vector decomposition, single value decomposition. Word to parse tree neighbors, there's a ACL paper on this, which basically, given a word predicting either the parent or child of a word in a dependency parse tree, this way you generate word embeddings where neighborhoods are more like, sibling entities instead of just general semantically related terms. Entity neighborhood list, this way you can do entity set expansion. And node random walk path in the graph, you can basically do like creating embedding nodes for network. This is what eWalk is doing. Okay, and then limitations of this kind of word embedding models. First one is ambiguity. So say if a word has multiple meanings, well, a lot of words have multiple meanings, the embedding will reflect the average of these senses in the embedding space. Debuggability is just something I can come up. So if something fails, most people think it's a black box. Doesn't know how to debug. Well, sequence data, so it doesn't handle the sequential structure of language words, words in the language. And if you want to do something like that, well, some speakers later on this afternoon are going to talk about models that handle that. Takeaways, word embedding techniques, nothing more than explicit or implicit matrix factorization. Co-occurrence matrix is the core element, and it's a feed-forward network. Training is just using backpropagation. Loss function I didn't talk about is cross entropy, and training can be made more efficient using hierarchical softmax negative sampling, and word embeddings of equal quality as word to backend, and actually obtained by using techniques like singular value decomposition. All right, thanks.
So can you compare why this with matrix factorization with SVD? Why you would prefer this over? Do you necessarily have to prefer which one to use?
So one thing is for SVD, you have to actually have the matrix to do matrix factorization. With word2vec, you don't actually have to explicitly have the matrix. You're just passing words, input words, output words. That way you can make it really efficient. So you have a million words in vocabulary. You don't want to build a matrix of a million times a million. There are experts.
Does that mean it's computationally more efficient?
Yes, it is computationally more efficient.
How do you evaluate these models?
There are so as you would evaluate the similarity measures between words, traditionally, like words in 353, those kind of predefined word similarity benchmarks. And there are also, you can plug it into classification or clustering, and then just evaluate the results of downstream applications. Other ways to evaluate.
But how do you, just one follow-up, how do you determine the dimension of the number of nodes in the hidden layer? That's
basically, 500, 1,000, and after you increasing the hidden layer to a point, it won't significantly improve the performance of the model. So then, unless you have significantly more data, going from 1 gigabyte to 1 terabyte, maybe, you can improve this hidden layer. Otherwise, just stop somewhere.
is that a function of